use different colors. We measured resistance, or if you like, this was called the potential probe. Let me write its name. This is the potential probe. And we denote the resistance we measure through these terminals as rho XX. And we also had another probe here where we measure from these two terminals, or these two, it really doesn't matter. Rho XY, and this was the whole probe. Okay. And what we got when we measure rho XX and rho XY as a function of the magnetic field turns out to be something like this. Now let me draw rho XY first. This is what we get. First, as we increase the magnetic field, as expected, the resistance, the whole resistance, increases linearly, because if you remember, rho XY was given by such an expression. So, as we increase the magnetic field, in the classical regime, we expect our resistance, and we denote it by rho, but it's really resistance, it's not resistivity. But since we are talking about a sheet resistance, it's more customary to use rho rather than R as a symbol. So as we increase the magnetic field, we see a linear increase, and then we start some small steps forming. So it starts forming these wiggles, and then at sufficiently large magnetic fields, we start observing such steps. And the interesting thing is basically not the formation of the steps, but when you look at these differences. Okay? So let me see if I have the exact chart. I want to give you some numbers. Well, it really doesn't matter, but this difference, or I should say, not difference. So the value of this guy is exactly, let me see, let me check the number, 25812.807.55718 ohms. And as you go down, this guy will be divided by a certain integer number. Although it's not clear in this graph, I have really done a horrible job drawing this, actually. Let me fix some of the features to make it more apparent. So this is going to be more like this, and this. Sorry, it's rather difficult to draw. The value here is half of this value, and the value here is 1/3 of this value, and the value here is 1/4 of that value. And the precision that we have in this measurement is down to 10th figure. And this is extremely robust. It doesn't change. As long as you have a silicon MOSFET, no matter how many different samples you have, always when you measure it, you get accuracy down to this digit. So this number seems like a universal number, and indeed it is. If you write down the expression, you will see that the number that we have here is exactly h over e squared. Okay? And now that's very curious. How does that happen? And last time our discussion was actually regarding how really that happens. So there are several aspects to the story that we build up progressively as we come to this point. One of them was the Landau levels, which plays an extremely important role in understanding of the quantum Hall effect. Then we discussed edge states. I'll talk more about it. And then disorder plays a significant role. And all of these, as we'll see in a moment, are binded together in a more general formalism. And that was our discussion about the Berry's phase and adiabatic approximation. So first, let me show you how we end up with such resistance plateaus, okay, and such resistance quantization. Then I'll explain the physical origin of how we end up here. So the simplest approach is this. Let me use this pen. Oh, I forgot to show the rho XX. Rho XX basically starts with a certain value, which is the potential across here. That's also very interesting. It diverges rapidly after certain magnetic field. Okay? And then at these points, it spikes. The points where it corresponds to these transitions between each plateau. Okay, so that's this spikes. Okay. Now let's continue with developing a fundamental understanding of why this happens. So remember, we are dealing with a 2D electron gas. And we have a magnetic field applied to this 2D electron gas, which means under sufficient conditions, by sufficient conditions I mean low temperature and high magnetic field, we should be able to see Landau quantization. Okay, so in a way, my electrons should follow these circular orbitals under strong enough conditions. Okay, so the energy levels are given by h bar omega and plus 1/2, and n is start from. And these are the indices of each Landau levels. And then each level contains n number of states. If you remember, it's they're degenerate states, and the number of states are given by the total number of flux that goes through the device divided by the flux quantum, which was given by h over e. So this is the, we have done this before. So when we draw the Landau levels, this is sort of what we got. So energy, and this is the density of states per each level. And this is what we got. So for each level, starting from 1 to going to infinity, the energy separation is h bar omega, and the omega was given by EB over m, and each level could hold n electrons decided by the area of the device times the magnetic field. Okay. Now what I'm after is finding an expression that gives me sort of this. So I'm going to do some sort of quasi-quantum, quasi-classical approach. So that rho xy is given by this expression, B over NE. Okay. And this is the density of electrons. And I know that when I have this strong quantization condition, the density of electrons will be determined by the density of electrons in each Landau level times the filling factor, which gives me how many Landau levels are filled. So my filling factor, that's defined as V, gives me how many of the Landau levels are filled. So for this case, for instance, I have 2 Landau levels filled. So my density of electrons will be given by N over A. This is the density of electrons at each Landau level, times the filling factor, number of Landau levels that I fill. So this will be the density of electrons. Simple, right? Is it clear? So density of electrons that I have in each Landau level will be given by N over A. This is, I'm looking at the density. So it's given by B times E over the Planck's constant. Then if I multiply it by the filling factor, which gives me how many of the Landau levels filled, then I'll end up with the total number of electrons, density of electrons in my system. So I can replace this expression in here. Okay, so my rho xx is going to be B over V. Now I'm going to write that expression, this one, explicitly. B over H times E times E. And yeah, I have V here. Okay, the minus sign. Then B's will cancel. I end up with H over E squared times 1 over V. Well, I got the result that I was looking for. That was quite simple. I ended up with the von Klitzing constant. That constant is named after the guy who first discovered the quantum Hall effect, 1981. So the rho xx is given by H over E squared. This guy? So this number of electrons in each Landau level is given by B times A. So this is an arrow. So this is given by B, A, H times E. Okay? So I'm looking at the density, so I do N over A. So I have N over A, which is equal to B E over H. Right? So I just plug in B E, so this is B E over H times V. I plug in this expression here, which gives me that result. No. This flux quantum is H over E. This is flux quantum. So let me write it in a more explicit way. Okay. Now this von Klitzing constant is that number. It's the definition of our resistance value we use today. So all the resistances that you get are calibrated with respect to a quantum Hall device. Okay? That resistance value defines 1 ohm actually. So 1 over this value is 1 ohm exactly. So this is the SI definition of an ohm, and it's commonly used in devices that requires precision and constant checking of the resistivity or resistance. So it's very simple to achieve, and this thing is extremely robust for any such system. For silicon MOSFETs, when you form a 2D gas, and you don't have to go to these really high magnetic fields. You can work with much lower plateaus, for instance, much higher Landau levels. You'll get 1 over V of that value, and that value will be the reference of your resistance. Now, before writing down more equations, because this shows sort of where this quantization comes from, but let's try to develop a more formal understanding. Let's try to have a better understanding of how these quantum Hall states form, and let's try to understand why they are so robust, and we see them in 2D electron gases. Now, I'm going to draw several pictures. Now, when we have this 2D electron gas near the Fermi level, we are going to have, so this is energy, this is density of states. You're going to have all these states filled up till the Fermi level. So it's going to act as a metal. Now what I do is I apply magnetic field. So at moderate magnetic fields, this is what I'm going to get. So this is my Fermi level. And then at very high levels of fillings, I'm going to have modulation in the density of states. But when I exceed a certain magnetic field, this is what I'm going to end up with. I'm going to form Landau levels. Okay, so this is going from a 2D electron gas that's completely free to move. There are lots of available density of states. And then as I increase the magnetic field, these electrons will start orbiting around certain trajectories which will affect the density of states. But under the correct conditions, which is defined by low temperature and high magnetic field, I'm going to form the Landau levels. And now the separation of these Landau levels, as written there, is determined by h bar omega. And again, as written there, h bar omega is EB over m. So it depends on the strength of the magnetic field. So still, my Fermi level hasn't changed. It lies here, okay? Now, as I keep increasing the Fermi level, that's what I'm going to see. So I'll continue from here. This is still my density of states. This is the energy, and this is my Fermi level, okay? Now, let's say I increase the magnetic field in such a way that I double the spacing. So this lowest energy will stay there. Okay, and now since I doubled it, these states will be moved above the Fermi level. So see, I only ended up with 2 Landau levels below the Fermi level, which defines that I can only fill up these states. Okay? So if I keep increasing the magnetic field, this will go above the Fermi level. So I'll end up with a single Fermi level, single Landau level, which will be exactly this point. So as I increase the magnetic field, imagine that I have multiples of Landau levels compressed together since the magnetic field is low. I'll have small steps, okay? And as I increase the magnetic field, as a number of Landau levels decrease, these jumps will become more prominent because now I'm dividing this number by smaller filling factors, 1/3, 1/2, and then finally I'll end up with the exact von Klitzing constant, which corresponds to a single Landau level under the Fermi level. Okay, so this is more of a picture of how this thing evolves. But still, there is one missing element in this whole story. As I mentioned in our previous lecture, if you consider these very sharp Landau levels, as we have solved earlier, then these jumps, these plateaus shouldn't exist. Because as soon as I pass through the Fermi level, all of the states will be filled, and I shouldn't have any such plateaus because there are no electrons in the bulk to conduct the electricity. There are no available states for electrons to scatter, if you like, another way to look at it. All the electrons are involved in doing these circular orbits. So there are two things that I started discussing last time. One of them is the edge states. The other is the disorder. Now, disorder is quite important for the observation of quantum Hall effect, especially you must have disorder in your system to be able to observe these plateaus. Disorder can be anything. It can come from impurities in the sample, which inevitably will be there no matter how pure you make your system. In any device, you will have some impurities, some defects. So there will be some disorder coming from that, some disorder from the temperature fluctuations, and so on. So this disorder, the net effect of the disorder, will be broadening of the Landau levels. Okay? So the actual Landau levels are not infinitely sharp energy states, but they are like a Gaussian-shaped energy states centered around the Landau levels. Yeah. I'll explain that. Disorder is easier, so that's why I first started with disorder. Okay, now, because of this broadening, now let's rewind the movie and replay. So let's take a look at this condition where I have this broadened Landau state, this broadened energy state, crossing through the Fermi level. This is what will happen. So this is the density of states again. Energy, this is my Fermi level. And this is exactly one of the Landau levels. Okay, I'm not going to draw the others. So now, rather than a single level with multiple degeneracy, I have a level that will be partially filled as I cross through the Fermi level. So this is like the conduction band, right? I have lots of extra available states here. So this means there will be conductivity, and this explains why this resistance in the XX actually drops. Also, it explains why for a range of magnetic fields that certain value of rho xy persists, because as I enter through this broadened Landau level, it takes a certain amount of magnetic field, B, to cross this whole broadened level. Okay? Unlike this case, the red case, the transition would be sudden, but now this whole thing will take some B to go through this E. So once this passes through here, let me draw another frame. So this is some delta B later. Okay. This is what I'm going to have. So my Fermi level lies in the mid state, just like a semiconductor. So this will be completely filled. This will be completely empty. But since it's above the Fermi level, there will be no electrons in that state. And this will be completely filled. No conduction. So as I pass through this region, there will be no electrical, there will be a certain resistance forming. So that's the point where actually I make a transition from this point to this point. Is it clear? We did a lot to come to quantum Hall effect, but once you collect everything together, actually it's formed from a couple of very basic understanding of motion of electrons under the magnetic field. Okay.
So in the presence of disorder, the bands change the shape to this.
So we don't have bands here. These are Landau levels, and they're extremely sharp levels that are defined by h bar omega, right? And there are n number of electrons in each level. They're extremely sharp degenerate levels. But when you introduce disorder, as you said, there will be broadening of these levels, because the electrons are now, the ideal picture we had is all of the electrons are making this very beautiful circular orbits. The area that is defined by these circular orbits are integer multiples of h over e, right? So that's why we have this quantization. As I increase the magnetic field, as I cross, the loop size will enlarge, so I'll have larger orbits. So that was a perfectly beautiful picture. But now imagine we have a disorder. Now it will affect the way these orbits will be positioned. And this defect, this disorder, will have its own electrons orbiting around itself, which will destroy which will make certain energies around that disorder to shift up, certain ones that are away from that disorder to shift down, so that energy will be now not as sharply positioned thing at a certain energy level, but it will be slightly broadened. And there will be thermal fluctuations that will inevitably have, which will make these orbitals to wiggle around a little bit, which will change their energies slightly. So that these factors result in broadening of these extremely sharp Landau levels. And that's why we end up with these plateaus. Now, but still, yes?
What will happen with further increase in magnetic field?
That's a very good question. Well, I don't know, because there are samples. I don't think anything will happen. In terms of integer quantum Hall effect, in the framework of integer quantum Hall effect, but then you'll start inducing electron-electron interactions, because now the electrons will have more complicated paths as you pass beyond certain magnetic field, which initially we had certain assumptions on, okay? Then once you go about that, we'll go into the regime of fractional quantum Hall effect. But at this point, it's not something that we'll look at.
What do you mean by this high magnetic field, and what should be the field you are getting?
Well, it depends from sample to sample, but typically for silicon MOSFETs, we are looking at 10 Tesla already.
Okay, so like we increase magnetic field, and we observe that we have only one down level below Fermi. So, like, is this a condition that there should be some levels below Fermi level?
For you to have this?
Yeah, exactly. I have to.
Yeah. Well, yes.
Okay, and in this case, we introduced defect, and it is a broadening of the level.
Yes, exactly.
Fermi level was lying in between that broadened level.
In this condition?
The before condition. It was lying
So
in the
it is, yeah, it is within the.
How this transition I don't understand.
So basically, all I am doing from this picture to this picture to this picture is changing the magnetic field. Okay, as I change the magnetic field.
If you want to change the magnetic field, and this Fermi level is lying between two Landau levels.
In this picture, it's within a Landau level. As I further increase by delta B, now it's lying in between Landau levels, broadened Landau levels. Okay. Any other questions? Now, this is not the whole story. Again, edge states. Now, if you remember last time, I introduced edge states. So the idea was this. I have a sample of certain size. Okay, I'm looking at it from the top. And the electrons in the center are doing the circular orbits. But this system has its edges. So at the very edge, an electron will try to do this circular orbit as well. But before completing the full circle, it will hit the boundary of the sample. So the only scattering it can make is like this, but the magnetic field, as it bounces from the edge, the magnetic field will redirect it in the original trajectory. So you will end up, let's say I have an electron at the very edge, which tries to make the circular orbit. Every time it hits the boundary, it will scatter back and back and back and keep doing this orbit. So unlike the electrons in the center, this guy will be moving forward because of these edge scatterings. Okay? And the only direction that it can move is this way because of the magnetic field that I applied, because any event that would try to push it in the reverse direction will still put it back into the same trajectory. If it scatters into the center, then it will do this orbit. So it really, then an electron that lives at the edge of this 2D electron gas has really no chance but to move in this direction. Now let's look at the other edge. This time, because of the magnetic field, same rotation angle, my electrons will be doing the same thing, but this time they'll move in the opposite direction. And same thing that I explained applies to the electrons here. These electrons must move in that direction. Any scattering event that would require it to go backwards will vanish immediately to restore its motion in that direction. Now these are the formation of edge states in a system that in a 2D electron gas under strong enough magnetic field. So all of a sudden, the bulk is an insulator because all the electrons are doing these circular orbits, but the edges are conducting. So at the edge, I have a conduction. But in an ideal system, any number of electrons that travel in that direction will be equal to any number of electrons that travels in the opposite direction. So overall, I'll have no net current flow. Okay? Now, let's try to develop a more formal understanding of how these edge states, they are called chiral modes. Okay? So the chirality comes from the fact that they can only move in a certain direction under a certain rotation angle. So these modes are called chiral modes. Now let's try to understand how we can reach to this result that we derived here in a more formal description, in a more quantum mechanical description of the system. You guys have any questions before we continue? So it will become more clear how these edge states will be responsible for the features that we observe in quantum Hall effect. Now, I would like to draw the potential distribution, let me say E, with respect to position x. And these are the boundaries of my system. So when I look at the middle part, I'll have an equipotential. Indeed, as we'll see in a moment, well, actually we sort of discussed, this is slightly further from the truth because we have disorder. Actually, there are potential fluctuations in here. But at the moment, we are only interested in the edge mode, so we shouldn't worry too much about the edge states. Now I have these harmonic oscillators that are cut in half at the edges. So exactly at the edge, I'm going to have my potential rising up like this. Okay? So the Hamiltonian will be something like this. 1/2, 1/2m px squared plus py plus ebx squared plus v of x, which is this potential. So this is the usual Landau Hamiltonian that we have written in this Landau gauge. And this is the potential Vx that we have for that system. Now, if we look at the length scale of this guy, it's typically a very small region. It's smaller than LB, which defines the radius of that rotation. So it's on the order of or smaller than LB. Okay. So what I can do is I can say, okay, this function can be approximated by such an expression. So I can write my v of x as an expansion around that point. So I'm going to have v of capital X, let's say this is my capital X, plus del v by del x, x minus capital X, plus some other terms. Okay, so this is my constant term. Okay, this is constant. I just did a Taylor series expansion. And then this is the term that defines the slope of this boundary. Okay, so I just choose a generic function, and I have the Taylor expansion because my LB is a smooth function in a very narrow region, and I'm trying to understand how my electrons will move under such a potential with magnetic field. So it's the magnetic length that we define for electrons moving in under magnetic fields. So its value is so because the idea here is my electrons are following a certain trajectory, okay? And if my potential does something like this within that range, then this Taylor series expansion will be meaningless, because now I have to solve the motion of electrons using this very complicated potential. But what I am saying here is this, that potential function varies very smoothly. Okay, so it is a very gentle function, this is my assumption, within this length, LB. So I can do a Taylor series expansion, which will simplify my algebra significantly. Indeed, I reduced this to almost a straight line, okay, because thanks to this length defined by LB. Okay, so what I'm saying is essentially the potential energy within the length of LB changes very smoothly. So I can approximate any function within the first two terms of a Taylor series expansion. Okay, what was I doing? Now, of course, I have states that are located along the y direction, okay? And velocity, drift velocity of electrons that are traveling in this and that direction will be given by minus 1 over EB del V by del X. And that's indeed straightforward to see, because I'm after the force. So this expression is basically the force that's acting on a charged particle, right? So force on a charged particle moving under magnetic field is given by this, and force is that. So I already know the direction of my magnetic field, the velocity of, velocity of my electrons. So basically this term will give me the velocity of my electrons. And that's a very clever term, if you think about it, because this, in a way, defines the slope of the of this potential energy here. And on this side, the slope will give me a negative number, which gives me one direction of the electrons. And here it will give me a positive number, and it will give me another direction for the velocity of my electrons. So in a way, this expression defines the direction. It already shows me the direction of the electrons that are near the edge travels. Now, I'll solve the whole equation. I've written it a little bit complicated. So let me see. Let me get rid of this part. Now let's define a vector current, okay, which will be given by minus EV. Okay, so it's current flowing along a certain direction, which can be written as such. And MV is P plus EA. right, from the very early treatment that we made for the Landau gauge. So what I'm going to have for the current is such an expression, minus E over N P plus E A. Okay. Now, let's switch gears. I mean, this was a classical expression, but I want to do a quantum mechanical treatment of the system. And sort of what I'm after is the expectation values of these guys. So what I'm going to do is I'll switch to Dirac notation. Now, the states of the Landau levels are given by N and K. Then I'll write down the operators for these quantum objects, and then again N, K. Okay? So this is the expectation value . This whole thing is the expectation value for this total momentum of the object. And this will give me an expression for the current that's flowing through the system under magnetic field. Okay? Now, I know that this guy is x, b, y hat. Okay? So, I'm going to write this current expression as such, E over M, and I have to sum this whole thing over the field states. So I don't want to include empty Landau levels, obviously. I want to do this summation up to the field states. So what I'm going to have is something like this, I n k minus I h bar del plus E x b y hat phi n k. All right. Now we'll get some simplifications. First of all, I can look at what Ix does. As you will see, when we look at Ix, I can write this expression as so n goes from 1 over v, and then I sum everything over k. I have nk minus ih bar del y del x by nk. And this will give me 0. And that's not difficult to see. So this is at the quantum hole plateau, because I already know that along the x direction no current flows from the measurement. So I set this to equal to 0. That's the experimental observation, and in it it's not difficult to show that from the harmonic oscillator potentials I'll get 0 for for quantum harmonic oscillator wave functions. It's not difficult to show that this whole thing will give me 0. So this is consistent with the observation. No current flows in the x direction when I reach to a plateau. Of course, I'm interested in y, the current that flows in the y direction. So I have E over M n equals 1 to v, sum over k. Then I have phi nk minus I h bar del y plus exb phi nk. Then this is equal to minus E over M n equals 1 to v sum over k and phi nk h bar k. If you remember this guy, when applied on the wave function will give me h bar k plus e b x phi n k. So this is just a constant that I can separate this equation into two pieces. So what I'm going to get, also there's this guy, okay, this x. So what I'm looking at here is two things. One, phi nk with h bar k in the front, plus eb phi nk x phi nk. So this guy, this is psi, it's not phi, I keep saying phi, but it's psi. Okay, this is the expectation value of x in the harmonic oscillator, but we already know the answer to this question. It's sure. Well, I tend to write explanations more. Okay. So this whole thing is expansion of this guy. So let me continue down from here. I'm going to have E over M. Okay. Then again, sum over n equals to 1 to v sum over k. Then I have h bar k phi nk phi nk. Okay, plus now I have e b x, and we know the value of this guy. It's h bar k over eb minus m e over e b squared. If you remember, when we solve for the harmonic oscillator potential, that's the origin of oscillation for the harmonic oscillators that we had. So let me finish this before we give a break. I'll get rid of this part. Now finally what I'm going to have is something like this. Iy is minus e over m. Then let's see. I think I forgot a minus sign here. So this times this will cancel out with this guy. Okay. So sum over k. I'm not going to keep this one because these indices must give Kronecker delta, which is indices of these guys must be equal to each other. So I'll get a 1 out of that. So h bar k minus this h bar k will give me 0, and I'm going to have minus m e over this e will cancel with that one. B will take one of the b's down there. So I'm going to have m e over b. And again, I'll have the same expression which will go with that one. So the final expression is going to be something like this. EV, which is the number of filling factors that I'll have from there, sum over K E over B. Okay. Now, this is the current that flows in the y direction, but there are a few more things that we can do here. Now the summation over all these states will give me n, which is basically, because neither of these actually depends on k, nor neither E nor B, but this summation will give me BA H over E, number of electrons in the states. Then I can write this expression, whole thing as such. EV, okay, E times A divided by H squared. Finally, let's switch to current density. So I over A will give me J. Okay, so I'll get rid of this geometry dependent parameter. I'll end up with times V E. So the current density along y direction will be given by E squared H times V times the electric field. And that should look familiar. This guy is conductivity. So 1 over that will be H over E squared times 1 over V, which will be rho. So we ended up with the same expression that I have done in the beginning. That we started from a classical expression. This is von Klitzing constant. Okay, so let's give a 10-minute break and then we'll continue. I'll finalize our discussion.
We don't have any E here, so it's V expression, the box expression. This V. We have V here.
Yes. That V is the filling factor that I got from this summation. Okay. So, sorry, you're right. So I should have V here. So this summation basically gave me that V filling factor.
from Golding.
Explode one. The other one slowly burn. It's not exploding. It's really not exploding. Explosion is the explosion contacts and crystal is destroyed. Well, there's conduction, but when we started the resistance it was like few hundreds of ohms or kilo ohms, and then gradually it increased and increased and increased. But no, it's still working. In the end, it was like 100 kilo ohms, and then at that point we stopped and checked the device. The gap between two terminals was like etched away. There was a very thin connection between them. So probably
This time we have successfully lifted off as well.
oh yeah, we can do the other parts. So problems with Navid.
Yeah, he was already said that. No, I really.
He's wasted our time and gold.
So now we can go with the both, right? We can go with the optical lithography and the e-beam lithography.
Well, e-beam lithography is much better because it produces much better crystals. I'm sorry, much better devices. So we'll keep making devices using e-beam lithography when we're there on silicon dioxide.
We have lined up the asylum,
Mhm.
the photography part, and today we will start the asylum part.
Okay.
But we will start with the enlistment and then.
Mm-hmm. Okay, let's continue. So Now there's one last thing that's remaining to be explained. Why these quantum Hall states are so robust. What allows us to detect these quantum Hall plateaus down to 10th digit precision or 8th digit precision. Now, we partially answered this question. One answer is this. Now, even if you have disorders in the system, in essence what determines these plateaus is the edge states. Okay? This time I reverse the magnetic field. So I have my electrons that are flowing from one edge to the other edge. And also I have a disordered landscape. So there are lots of electrons doing these nice orbitals, but some of them are following weird trajectories because of these disordered states, but still they have to follow the trajectory that's defined by the external magnetic field. And other electrons at the edges are basically flowing forwards and backwards. And the robustness of these Hall plateaus comes from the fact that these two edge states, to a certain extent, are disconnected from each other. If you want an electron to reverse its direction and go backwards, which will inherently introduce that resistance plateaus to change their values, because the number of electrons that goes in certain direction is well defined, and number of electrons that goes the other direction is well defined. It's determined by the potential that you apply between the leads. So if you try to take some of the electron population and reverse its direction, then the scattering events that has to take place must take this electron from here and put it across the sample so that it can travel backwards. But when you consider the sample sizes, we are talking about at least microns, tens of microns. And an electron that has a Fermi wavelength of 50 nanometers or so, going from here to here is exponentially suppressed. So for every micron or every 50 nanometers that you travel, probability of an electron scattering from here to here decreases exponentially. So the probability of finding electrons within the first micron from the edge already approaches to zero. Same applies to this edge. So this tells us that any electron on this edge that moves in this direction will most probably keep moving in that direction. An electron moves in the other direction, will most probably keep moving in the other direction. So whenever you apply a potential difference to your sample, this will preserve the number of electrons traveling one way or another, which gives the robustness of the quantum Hall plateaus in a sense. So that's very important. As we'll see probably today, when we start discussing quantum wires and quantum point contacts, we will also see quantization of the conductance, but it's not as robust as this case because it doesn't have this topological property that's defined as here. Okay. So there are more general arguments that follows quantum Hall effect. I mean, the big fuss about quantum Hall effect is possibly not because the quantum Hall effect itself, but its implications and what people have done to understand this phenomenon. One thing that I'm not sure if I should talk about it, but at least you should be aware of that, is Laughlin argument. So this guy is a I think he has a Nobel Prize. He says this quantum Hall effect falls under this general category. So you can explain it as by topological considerations. Okay. And he devises this thought experiment. He says, okay, let's take a ring of a conductive material. Okay, so my electrons follow a certain path. And what I would like to do is I would like to apply an electric field radially to this ring. You may think that, well, how the hell are we going to apply an electric field that goes radially around? So that's what I want to do. Well, it's easy. What you do is you put a solenoid inside, and then you change the magnetic field B from one value to another. So the electric field will be, so let's stick ourselves to the radial direction, will be given by the rate of change of the flux. And the idea that he presents is, now let's start from zero magnetic field, so zero flux, and adiabatically, which means the motion of electrons will be much faster than the time scale of me changing my magnetic field from B1 to B2 or 0 to certain value. I'll bring it exactly up to a single quantum of flux, H over E. Okay. Now, his argument follows as such. He says, under this condition, I will take, so I have certain population of electrons, okay, assuming that I set them in such a way that certain population of electrons are traveling along this circular object. As I change the flux here, adiabatically from 0 to that value, these electrons will start taking a slightly larger but very well-defined orbital. And the population transfer from this inner orbital to outer orbital will exactly be given by H over E squared. So the change in the conductance will be exactly in the integer of conductance or integer of multiple of resistance. Now, if you think about this geometry, and I don't want to go into the details of calculation, but trust me with the result. If you look at this system, it has nothing to do with the whole bar geometry. But in deep down there, actually you can transform from this geometry to this geometry without doing anything, actually. So these two geometries are topologically the same. So based on these arguments, there is a whole different way of looking at quantum Hall effect and effects that have this topological properties. But at the moment, I think this much should be enough. Towards the end of the semester, I'll show you quantum Hall effect in graphene and its connection with the Berry's phase and these considerations. But for now, I think just knowing that quantum Hall effect by itself roots down to much complicated and much more rich physics than what we have seen here. Okay. Any questions? Okay, so I'd like to answer one final question, which you should have asked at some point. If you have noticed, we confined ourselves to 2 dimensions, and we never talked about 3-dimensional electron gases showing quantum Hall effect. So, quantum Hall effect in 3D. Well, no such thing exists. Okay, so the idea is, so I should write, it vanishes for 3D electron gas. Now, if you take a 3-dimensional object, the z motion of electrons will not be affected by the magnetic field. Right? Any electron that goes upwards in parallel with the magnetic field will not be affected by that magnetic field. But when we remove the confinement in the z direction, we introduce new states. So rather than now Landau levels, discrete energy levels, we'll have Landau bands that will be enabled by the z motion of the electrons. So if you look at the density of states per, so this is the energy. This is what we had with discrete Landau energies. But in 3 dimensions, these energies will form such bands that are connected. So these states will be able to fill up with electrons. And as a result, from this simple argument, as we don't have discrete energy states, when you tune the magnetic field, you'll just see some oscillations of the conductance, but no well-defined Hall plateaus. It will just be some Shubnikov-de-Haas type of oscillations in the resistivity. Okay, so it's basically because of giving another degree of freedom to electrons releases that constraint on discrete energy levels. Yes.
Specific boundary between 3D and 2D system.
Yes. Well, that's the way we define is if length in z is comparable to the Fermi wavelength of the electrons, then they are strongly confined. If you say this, then you remove the confinement. It's not in quantum regime anymore.
How about 1-dimensional?
We'll see it in 10 minutes. Okay, now that's pretty much it with the quantum Hall effects. Indeed, this, what we discussed is integer quantum Hall effect. And as Hamid asked, when you start tuning the interactions between electrons, or when you start applying large magnetic fields, then you enter into the regime of fractional quantum Hall effects. So rather than having discrete values for filling factor, you start getting fractional values. But we'll discuss that if time permits at the later stages of the course. Now, one last thing that's relevant to quantum Hall effect is, again, Shubnikov-de-Haas oscillations. We have sort of mentioned de Haas oscillations. But now, within the framework of quantum Hall effect, I think it will make more sense because we have seen these. So, just as a reminder, this is my rho xx. So, this is magnetic field. I have nothing, so my electrons don't feel the magnetic field at low enough magnetic fields amplitudes, and then it starts oscillating wildly. So it's the oscillations in the resistivity of a sample. Okay, and the formulation stems from considerations of the quantum Hall effect. I'm not going to derive this formula, but since I believe it's important in at least experimental physics or experimental characterization of materials, I'm going to write it down. So the formula is something like this: 4 times cosine EF divided by h bar omega times 2 pi squared kb over h bar EB times mass. This is, of course, the effective mass times temperature times 1 over sine hyperbolic x times e to the minus pi omega t tau q. This is quantum scattering time. This x is basically this, and it's customary to define this guy as d. And parentheses. So the same expression is in here as well. Okay. Then the amplitude of these oscillations are given by such an expression: a 8 rho xx as zero magnetic field times d times e to the minus pi omega tau q. Okay, so these are the amplitude of oscillations. Then now, what can we do with this thing? There are two important things that we can extract. One is the mass of the electrons, so effective mass of the electrons. Two, the quantum scattering time, tau q. And let me show you how you can do this. The first thing you do is you set up your experiment in such a way that you're in small magnetic fields. Okay? And in the small magnetic field regime, you take logarithm of both sides. Okay, so you take, this is what you write down, ln A over T, which is temperature, equals to some constant minus ln sine hyperbolic x. Okay. So if you plot, now let me do this assumption first. For small magnetic fields and large p-values, this expression will be approximately equal to x. It's not too difficult to show. So this means ln A over T will be proportional to 2 pi squared kb divided by h bar EB times m times t. Now, in an experimental setup, imagine you have a whole bar geometry, and upstairs in the PPMS, you connected your device, and you started doing these 4 terminal measurements. And as you start increasing the magnetic field, you'll start seeing these Shubnikov-Dehas oscillations, and assume that the temperature is large enough. Then all you have to do to figure out what m is, plot the amplitude of the oscillations divided by the temperature which you measure, and preferably it's a constant temperature, or you can change the temperature, it really doesn't matter. And then you have a certain magnetic field. Either you keep the magnetic field constant or the temperature constant, but people preferably keep magnetic field constant. So these are all now constants, and you change the temperature very slowly within this watch t regime, and you plot logarithm of amplitude divided by t. This is something you measure from the amplitude that you see with respect to the temperature. And the slope, so this constant times mass, will give you, that slope will give you the effective mass of electrons within your sample. So that's one way to see how within that regime, how your electrons, how massive your electrons are. There is another factor that we can determine, TQ, and the way to do it is, again, similar to what we have done here. This time, what you have is, so we are interested in the oscillation period, okay? Sorry, oscillation amplitudes. But this time we don't have such argument. And what we have is, again, that amplitude times B. Again, this is derived from the same formula. Sine hyperbolic x equals to some C2, some other constant, minus pi m star divided by E1 over TQ 1 over B. So what you do is you take the, so this is what I'm after. I know my magnetic field. I can, from this measurement, I know the effective mass, so I can plug in whatever values that I have into X. So on this side, these are all the things that I really measure and have value about. I know what my effective mass is, I know what pi is, I know what E is, I know the magnetic field that I apply. So if I plot this against 1 over B, from the slope, I'll get the quantum scattering time. So scattering events between these quantum objects, the electrons. So this is one experimental tool while you're working on a new sample that you can apply. Okay. And these Shubnikov-Dehas oscillations are also used to map out the Fermi surfaces of metals. So it's a useful tool. Okay. Now we'll switch gears and we'll start looking at other mesoscopic objects. So far, the mesoscopic objects that we dealt with were, in the case of at least quantum Hall effect, the electron's motion were somewhat confined by the external fields that we applied and so on. So now we are going to impose boundaries on electrons' motion. Okay, so what is a quantum wire? Let's say I have a conductive channel like this that is connected to a metal. That's always the case. Whenever you have a nanowire, if you really want to make a measurement on it, it must be connected to the outside world. So you cannot measure an isolated nanowire. Okay, so when you draw a nanowire, what you have to think about is the nanowire itself plus the external world. And the confinement limit is, now we have our length L, and this, let me see which directions I used for the sake of consistency. So this is my y direction, this is my x direction, and out of the board is the z direction. And the confinement, so width and also height, are smaller than the Fermi wavelength that I have. Okay. So, or you can say comparable as well. This omega W is the width of the wire, H is the height. Okay, so width and the height, and length is the L is the length of the nanowire. So, if you remember, this is given by, or 3 electrons, 4 over n, where n is the density of electrons. Okay. Now, let's try to understand how electrons would move under such a system. There are 2 regimes that we can define. Diffusive. In a diffusive regime, the length of the wire will be much larger than the diffusion length of electrons. Which means, let's say I have an electron here that starts its life. The scattering events that it will encounter will be so significant that the motion of the electron from source to drain will be diffusive. Okay? When I apply an electric field, it will encounter many scatterers. So the mean free path of electron should be much smaller than the length of my channel. That's the condition for diffusive transport. And if you think about it, this is sort of easier to deal with, but still we have to respect the confinement in x and y directions. Then we also have the ballistic regime. In this case, I start with this electron. It either performs a single scattering or no scattering at all. So it can travel very long distances within the material without doing any significant, without involving any significant scattering events. So in this case, this LD is either comparable or greater than the length of my nanowire. Now, for metallic nanowires, this is pretty much always the case. You can never find a metallic nanowire that has ballistic transport. And the reason is, in metals, basically let me see, the mean free path, so this LD is typically on the order of hundreds of nanometers. Okay, and sorry, tens of nanometers, and the Fermi wavelength is typically like extremely short, on the order of a fraction of a nanometer. So making such a short nanowire is practically impossible, because once you start confining your nanowire to metallic object to such dimensions, then, as we'll see in a moment, there are other considerations that we have to take into account. So you go to a regime where you start forming quantum point contacts. And for this guy, you must have clean semiconducting materials. And the diffusion length can go up to 50 microns. Indeed, in certain samples at low temperatures, you can have millimeter long diffusion lengths. So an electron before scattering can travel up to a millimeter. That's a huge distance. And Fermi wavelengths are typically hundreds of nanometers in this case. Okay. Now, let's look at the diffusive regime first. Now, let's look at our nanowire from the cross section, and it's typically, at least for solid state nanowires, it's typically embedded in an environment. So it could be either built in aluminum, gallium, arsenide nanostructures, or, for instance, you can have silicon nanowires that are grown on, I don't know, certain substrates. But regardless of whatever you have, it's embedded in an environment. So it can be air, it can be vacuum, but the confinement comes from the fact that the material you have here is different than what's on the outside. And I don't know exactly why, but one good approximation to the potential in this quantum wire is, again, a quantum harmonic oscillator. So when you look at the potential, rather than having very sharp boundaries like in the case of infinite potential well, you rather have smooth boundaries, because, again, I mean, I said I don't know, but my best guess is, because this is easy to solve, and also whenever you have an electron, its wave function is not actually terminated exactly at the boundary, because no matter what you do, there are, even if you have vacuum, this wave function will leak at least by a certain amount to the outside of the quantum wire. So modeling it with an infinite potential well is not the best idea, probably. So rather having a parabolic potential gives a better result. So that's what I'm going to follow. I'll say along the width of the wire, so when I look at the cross section, the potential is an harmonic oscillator. Okay? Any objections or any questions regarding that? So let's see what it gives us. So the Hamiltonian can be written as y squared plus m omega squared over 2 y minus yn squared. Okay, so this sort of gives me the center of that oscillation. Okay, and this is the typical Hamiltonian for a quantum harmonic oscillator. Now, following from the Landau equations that we used, we know that along the x direction I should have plane waves propagating, and along the y direction I'm going to have such a wave function. Okay. Then the Hamiltonian in xy plane is going to be something like 1 over 2m py squared plus m omega b squared divided by 2 y minus yn prime squared. I'll explain why I have a prime there. Then h bar squared kx squared omega 0 squared divided by 2m omega b squared. And here this yn prime is equal to yn minus omega 0 squared divided by omega b squared times b. And here omega b is square root of omega 0 squared. So it should be c plus omega c squared. Did I mention that I have applied magnetic field? So I apply in-plane magnetic field. Sorry, I forgot to mention that. Sorry, not in plane. It's pointing out of the board. So there's as usual, we have a magnetic field. Okay. So then the energy values corresponding to this guy is going to be something like this. So it will depend on B. It's going to be h bar omega. I think I screwed up something, but so omega b, and or let's continue with j plus 1/2, and j will start from 1 to 0 to 1 to 3, and it will go on like this. So in the diffusive regime for quantum wires, this is what we are going to get for the resistivity, rho xx, and I have magnetic field here. So I'll have certain value, then let me see. And this happens, so this is like 8 Tesla, 6 Tesla, and then there's 4 Tesla, somewhere here 2 Tesla, and there's like 1 Tesla. Sorry about the scale, 0 Tesla. Okay, so here J is the number of occupied modes, and it's given by 3 pi 4 n omega 0 2/3 h power 2m 1/2 omega b. So this is sort of 1D analog of the quantum Hall effect. Now these ballistic electrons will again follow the edge states, but the diffusive electrons will follow these edge states, and beyond certain value you'll see these large fluctuations in the resistance of your sample. This was just a side note that I wanted to share. Our actual focus is going to be on ballistic regime, because this is really where mesoscale effects starts taking place, and this regime is a regime that you cannot explain with classical terminology. So what we'll do in the next lecture on Friday, we'll try to understand how a ballistic electron that lives in a 3D world can be transferred into the wire and from the wire to the drain side. So we'll be looking at this whole system in general within the ballistic regime. Any questions before we finish? Unfortunately, we have to schedule our midterm sometime soon. I'm thinking something like, I haven't checked my calendar, but I always had 10th of December in my mind, which is Monday. Well, something in the week of 10th of December. So we have, well, it's a Saturday. Do you want to come here on Saturday? Well, okay, let's...
Because we have to meet them.
Okay. All right, so I'll try to do it on 14th or 15th. I'll let you know.
And the midterm, the concept of the first midterm is...
Well, no, I'll not ask any questions from the first midterm, but I mean, we have been doing a lot of Landau levels recently. If we think about the last midterm, since then we have spent a lot of time on Landau levels, and then we spent some time in the adiabatic approximation and Berry's phase, and then we have done quantum Hall effect, and by then we'll finish quantum wires and quantum point contacts. Then we'll look at transport regime in different electrical transport in different systems. So probably we have plenty of things that I can ask in the second midterm, so there will be nothing. Yes, I'll assign probably 2 homeworks.
Same way that we, in the first midterm exam.
I don't know if you enjoy it that way. We can do open book again, open laptop, open everything, no discussions. Yeah. Okay. But I mean, you now at least must have some understanding of what kind of questions I ask and what I expect